Welcome to the 21st class time series of lecture videos. This is our first video in that series of lecture videos. We're going to briefly discuss sulfur analogs of alcohols and ethers and then move on to alkenes, which are also known by a more common name, olefins. As I said, we will only briefly discuss sulfur analogs of alcohols and ethers. Sulfur is directly beneath oxygen in the periodic table. Instead of methanol, you could have methane thiol or other alkane thiols. So you simply have an SH instead of an OH. Instead of dimethyl ether, you could have a dimethyl sulfide or some sort of other dialkyl sulfide. What's interesting about sulfur is it forms sulfur-sulfur disulfide bonds. So of course oxygen does this too, however those peroxide bonds are fairly unstable. They can decompose explosively. Our sulfur-sulfur bonds, on the other hand, are relatively robust, and in fact they are persistent, especially in things like hair. So here we have dimethyl disulfide, and you could think of replacing those methyl groups with other alkyl groups. So, like I said, it would be brief. We're switching gears to alkenes. We've seen alkenes a bit already. We've seen them as products of unimolecular and bimolecular elimination reactions. It's probably important to note that a given alkene, of course, is a carbon double bonded to another carbon. How many other bonds can we have to those two carbons? Well, 1, 2, 3, 4 different groups could be stuck on those two double bonded carbons. In ethylene, those 4 groups are all hydrogen. Here we've got propylene, which we also know as propene, so 3 hydrogens and 1 methyl group. Here we have 1 hexene. So again, 3 hydrogens and a butyl group. Of course, the longest carbon chain is 6 carbons, so it's a hexene. Here we have 2,5-dimethyl 2-heptene. And we could even incorporate, ideas of stereochemistry in there. So 3s-methyl cyclohexene is shown there. Now, of course, alkenes have geometries. There's hindered rotation around a CC double bond, and we'll talk about that in the next lecture video. But in terms of naming them, I'm sure we're all familiar with cis-trans conventions. However, sometimes it becomes difficult, even using cis and trans, to specify your alkene geometry. So there is a more specific way of naming for various alkenes that cannot be clearly specified with the cis and trans geometry. So that will be the next subject. Here we go. Here is trans-2-butene. We all know what this means because our methyl groups are our 2 highest priority substituents of the 4 different groups that we can have on these 2 double bonded carbon. And in terms of geometry, they're located on different sides of that double bond, so we say they are trans. Another way we could indicate this is we could say that this is E2-butene, which literally means the 2 highest priorities are on opposite sides of that double bond. Here we have cis-2-butene, where the 2 highest priority groups, the 2 methyl groups, are on the same side of this double bonded carbon. Another way we could specify that is Z2-butene. Here is E2-hexene, so we know that our methyl and our propyl group are our 2 highest priority groups on these double bonded carbons, and they occur opposite one another. So you could indeed call that trans-2-hexene. So what does E and Z stand for? Well, E stands for entgegen, which is German for opposite. Z stands for zusammen, which is German for together. The way I like to remember this is, it's German, so it's a little backwards. Apologies if there are any Germanophiles in the crowd. But yeah, geez, this E alkene looks like a Z, and this Z alkene kind of looks like an E. So there you have it. And of course, the Z and E refer to the two highest priority substituents on our alkene. This would be difficult to, specify with cis and trans nomenclature because we have 3 alkyl groups. Yes, I suppose one could assign priorities to the different alkyl groups. However, we call this Z 3-methyl-octene because the two highest priority groups, the butyl group and the ethyl group, are on the same side of this double bond, and our two lower priority groups, the methyl group and the hydrogen group, are on the other side. Here we have E,1,2-dichloropropene, so the two chlorine groups are on opposite sides of that double bond. They're the two highest priority groups. Alcohols always take priority over our alkene bonds, so here we have Z 3-methyl, 2-butene, 1-ol. Here we have 1,4-pentadiene, no alcohol in this, but hey, we've got 2 alkenes. That's interesting. All right, with that, I guess our lecture video is our first one in this series is going to be a bit short. Hopefully the other few in this series will also be fairly short. So good luck with the question, and I'll see you in the next video.